The last example we were using the recursion function to solve the problem is Tower of Hanoi. So what is the Tower of Hanoi? Actually, that's the game from 1993. A French mathematician have that. At that time, actually, they reward for here you have 64 golden discs. So they ask you to follow some rule to see if you can move the whole thing from A to C. But they have some rule. One thing is you only can do the one disk at a time. And also all the time, the larger disk should be on the bottom. So that means no larger disks can be on the smaller one. So if you can do that, actually at that time, 1984, you can reward $34,000 like today. So can you do that? So the game is supposed to move all the disks one by one only. So you only can move one at a time from one pile to the other. And also you never placing a larger disk on the top of a smaller one. So if you can do that, you will win $34,000. So the first thing before you can do that, so you will have the link I show you in the lecture pages. So you can practice on that. Okay, so after you open the link, you will see the application look like this. They allowed you to do at least, you need to have 3 disks in the pile. So then at most, you can do 8. But we just see how can we do that. So actually here is the start. Here is the end. So at the end, you need to have 3 disks all move to the final one. But this one is the spare you can use for that. So we see here how we do 3. If we want to do 1, that's easier, right? So you see we just move the 1 here. Okay, but here we have 3. And all the time, your smaller one needs to be on the top one. So on the other hand, now the only choice, I need to move the second one here. So actually my goal is this one, the greatest one should be in the final location, right? So that's why now I can leave that now. See, I have the 1 here. So now I can move my biggest one now. So now this one is in the right location. And on the other hand, the first 2 is in the spare one. Okay, so now in order to have the rest of that here, so then we will need to move that smaller one first. So then we will have this. So then you will see if you want to move 3 of that, you will have 7 move. So now can we do 4? So actually on the other hand, in order to do 4, I need to have my 3 to come here. So that's why I can move the 4 come to here. And also earlier we did know how to make the 3, right? So that's why, but now since total we have 4, I need to have the 4 minus 1, the 3, not go to the final location. I need to target to here. So that's why here you will see that's move. Okay, so then each time you see you want to move 3, you need to have 2 in place first. So that 3 will be the target location. So now you don't need to worry because they are all the biggest one. So now here you see you move the 2 here. Then you have the 3 in place. And you can have the biggest one to come here. So now we can play that now. But now since you have 3, right? So that's why you see I need to put this one to here first. Okay. Then I can leave the 2 here. So then this one can come here. So that's why then I can come back to 3. Now I need to have 15 movement. So what we find out actually is no matter how many you have, so not even you have 5, right? So the first thing we need to think about 5, my target is this C. We will say the pile A, B, C. But one thing is if all my final I want to have 5 into the C. Actually, what I need to do is I need to have the 5 minus 1, 4 of that in the spare one first. Then I can move the 5. So earlier, right, do you know how to do the 4? I can because I just do that. So that's why we see here. So actually, like earlier we show you, actually for any n disk, you need to think about, we need to split that original problem into 3 steps. If I want to have n in the right place from A to C, okay, so then actually I need to have the first n minus 1 to go to the second, the spare tower first. So then after I have the spare tower B is right? So then I can have the last one, the n, go to A to C. So then after you're done, so then you have your n minus 1. So then you can find. Again, let me correct that. Actually, earlier from our application, their final one is here. But one thing is in my slide. Actually, here in the picture here, I want to show you. Actually, the final one they call B. So that's why here you will see a little different. So there actually is this one for when I want to move N. Actually, they are from A to B. So that's why the final one is B. So that's why you need to have the first N minus 1 from A to C. So using the final one actually become the assistant tower. So then your last one, and then you can do the biggest one, actually just right away start from A to the final destination. So then after you have the first move, have the n minus 1 from A to C, right? So now actually I just need to from C to move the n minus 1 from C to B again. So that's why you use the assistant tower with the A. Okay. So the most important thing is just sometimes maybe the the target, your final, either C or B from different example, they will be different. Okay, so then you just need to see which one is. But no matter which one is the final destination, the most important thing we know is whenever you have n disk, we just need to break down into the 3 parts. You have the n actually the last one. We just consider this last one. We just right away move from our original tower to the destination tower. So then actually on the top of n minus 1 before the n, we need to using the original tower to the spare tower. So then actually we're using the final tower kind of is like our assistance tower. So then of course after you can successfully move n minus 1, then you have n. Then you can replace n minus 1 back from the spare tower, then we move to our destination. So that's why we call that recursion function, right? Because you see n, I can break down, I call the recursion function twice. I call that n minus 1 one time. Then this one actually very clear, I just have one move. So then I have another n minus 1, I will just call the recursion function again. But one thing is, how should we write the prototype? So the most important thing, we want to display each move. So that's why here in our function, that's our function look like. That's our prototype. So we just call there the move disk. So this move disk actually they have 4 parameters. The first one tell me how many disks you want to move. So then we have 3 parameters. It just means the number of the tower. Just like earlier we say you have tower A, tower B, and tower C. So we just using a character to represent the name of the tower. You have your original tower, you have your destination tower, then you have your assistant tower. So then, right, we have the base cases. Our base case is what? Right, when n equal to 1, then I just need to move Okay, when n equal to 1, actually I just need to move the disk. So then you just call the disk name. So then you tell them from which tower to which tower. Otherwise, you will see here, then we will just move. Okay, so then here, if it's not n equal to 1, then I just need to call again. Because here I need to call the recursion function is move disk. So again, I just need to pass n minus 1. But here, from tower is the same. But the two tower and the assistant tower, they need to switch. Remember earlier we need to use the n minus 1 go to the assistant tower instead of the target tower. So then you see here we have the last one. The last one is the biggest one. I can just right away to make the move. So when we say to make the move, actually just print out the move, how they look like. So the disk, n is the number here. So that's from the front tower to the two tower right away. So then the next one we call the recursion function again. So that's why we have the n minus 1. So but we found the assistant tower to the two tower, then I'm using the front tower as assistant tower. Yeah, so you check if that makes sense. So most important thing is here is earlier how we break down our problem into a smaller one. But don't forget we need to have the base cases to make us to finish. So then if we write this one as our static method, they will look like this. So then here, right, so when I ask the user, just tell me how many number of disks you need to move. So then we just move. So we will tell them. So just according to the user n, so I call move disk. So this one, our two tower actually using the, yeah, this one we do the two from to and assistant tower, right? So so that's why we always find A. But this one, our destination is B. So then our assistant tower is C. So that's why they can print one by one. So then actually when we run this program result, if earlier we just show you, they only show you the move, enter the number of disks, so then they just show you the move. But still not enough, I also want to display total how many move, right? Right, so where should I display total how many move? So actually you can see here, total how many move, we need to have a count. So that's why here, this count actually is every time I go to the function to call, I need to have a count. So that's why we have the static count variable. So then when we start calling the first time, we set that equal to 0. And every time I call this function, I just increment by 1. And also you can find out, when we call every time we call this recursion function, actually we either have this move or this move will be displayed. So on the other hand, later when we display total how many move, actually that's mean total how many times we call this recursion function. So right, you can download this example. So then you can see if we run if the disk is 4. Yeah, earlier we just showed you that's the 15 move. So then this one we show you one by one how they move. Very similar to our example from here. You see this one, before you show their move, they will tell you the minimum move is 31 for 5. So then if that's 6, that's 64, 63. So then 7 will be 127. So that's also match what we do. If you run 5, then you will see there are 31 move. But I wonder how many times you can really run. You can all run this program and to estimate, to see how many days you can really run. So, but back to our question. Our question earlier is we want to find 64 disks. You see in the application I show you, they only have 8. But then let me show you really 64, how many times we need to run. If you noticed, so when we have a disk 1, we have 1 move. 2 disks, 3. 5 disks, 31. So if you kind of notice, they are actually 2 to the nth power minus 1. Right, so on the other hand, 64 disks, you need to have 2 to the 64 exponent minus 1. Do you know how long it is? That's so many years. So even our computer is fast, now you need to spend